In this lecture, let's understand startup file of a project. First, let's understand the importance of startup file, and later we have to write our own startup file for our project. Why startup file is required? So the startup file is responsible for setting up the right environment for the main user code to run. Code written in startup file runs before main. So you can say that startup file calls main. Some part of the startup code is target dependent. For example, a startup code may include the vector table, which is again the processor dependent or architecture dependent. Or the startup code may initialize the stack pointer. The way you access the stack pointer register of the processor is again processor specific. That's why you can say some part of the startup code is processor dependent or architecture dependent. In some cases, the startup code may have to turn on some coprocessors like floating point unit. For example, if the main user code is doing some floating point operations, then it has to be turned on prior to that. Otherwise, there could be an exception in the program. That's why if you want to enable any special peripheral of the processor or target, you can do that in the startup code. Startup code takes care of vector table placement in code memory as required by the ARM Cortex-MX processor. You know that initial code memory addresses have to be filled with vector table, isn't it? That should be taken care by the startup file. Startup code may also take care of stack reinitialization. I mean, you can alter the stack placement. Startup code is responsible of .data and .bss section initialization in main memory. That is very important. By properly copying data section from flash to SRAM and by properly initializing the BSS section in the SRAM, the startup code has to call main. Before that, startup code should not call main. Let's write the startup file for our microcontroller. We are going to do three important things in the startup file. The first one is to create a vector table for the microcontroller which we are using. Vector tables are MCU specific, remember that. After that, we have to write a startup code which initializes .data and .bss section in SRAM. And after that, we are going to call main. Let's head over to our workspace. Here we have our files. Let's create one C file. Let me call it as stm32 startup.c. Startup file can be created either in .c or .s as an assembly file, but let's create .c file. I just created the file. Here it is. If you don't have this MinGW64 command prompt, then no problem. You can create manually in the workspace. Let me open this file. First, we have to create the vector table. As I said before, vector table consumes initial addresses of the code memory, isn't it? And vector table contains handler addresses. We have got 15 system exceptions and 82 IRQs in this microcontroller. 82 plus 15 plus 1 is equal to 98 word addressable memory locations we are going to consume as a part of vector table placement in the code memory. That is 98 into 4. Totally, the vector table consumes 392 bytes in the code memory. So if you are wondering how did I get this number 82, you just have to go to your reference manual of your microcontroller, then search for vector table. This is a vector table for STM32F407 microcontroller. Here you can see that at the very first location should be reserved for the MSP, and the next location should be the address of the reset handler, and the next location should be for NMI. Initial 15 addresses will be consumed by the ARM Cortex system exception. So up to here, these initial 15 memory locations should carry addresses of various exception handlers of the processor. After that, the first IRQ, that is IRQ0, address of the IRQ0 handler. After that, it goes all the way to 81. That means 0 to 81 are IRQs. That means totally 82 IRQs. Let's move forward. So now how to create a vector table. So what is vector table? It's a collection of addresses, isn't it? Create an array to hold MSP and handlers addresses. In order to hold the vector table, we are going to create an array of U32 int. And this array we can later initialize. What is this array? This is the data, isn't it? Data of the program. By default, compiler will store the initialized data or initialized variable in data section. But that should not happen for us. The vector table should not go here. It should go here. That's why we have to instruct the compiler not to include the above array in data section, but in a different user-defined section. So we'll see how to do that. Let's get into the source file. This is our startup file, and here let me just use include std int.h and uint32_t vectors. This is an array, and let's initialize this array. I would do like this. The first entry should be the MSP value. We will place the stack at the end of SRAM. That's why let me calculate end of SRAM. Hash define, let's say SRAM start. What is SRAM start? 0x2000000. Let's consider this as an unsigned number. After that, hash define SRAM size. What is SRAM size? Let's consider SRAM1 and SRAM2. Collectively, it is 128 into 1024, 128K kilobytes. That's why SRAM end is, we can say, SRAM start plus SRAM size. Let's keep all these operands in parentheses. After that, define, let's call stack start at SRAM end. After that, let me use this stack start at the very first location of this array. Second element is address of reset handler. You have to follow this table. Second one is reset handler. We don't have a reset handler. Let's create a reset handler. Void reset handler void. This is a function prototype, and let's create somewhere here. This is the reset handler, and I'm giving the address of that reset handler here. This is a function pointer, but this is not a function pointer, so this is a value of uint32. That's why I have to typecast this. That's it. After that, let's see whether it compiles or not. Before writing everything, let's compile this. Let me go to the make file. Create one more target here. Let me call it as stm32 startup.o, and the source is stm32 startup.c. Here main.o, ld.o, stm32 startup.o. Let's make. Yeah, it went well. I would like to introduce one more flag. In the compiler flag, that is -w all. It will turn on all the warnings. Compile once again. Let me also create make clean, to clean the project. I mean to delete all unnecessary object files which are created. Let's also create one target to clean the folder. Clean is nothing but it will delete all object files and ELF files generated. It will make your workspace clean. It only keeps the .c and other required files. For the clean, I would use rm minus rf. Let me remove all .o files and also all .elf files. Let me run make clean. Yeah, you can see that all .os and .elfs got deleted, isn't it? Make all. Yeah, so the compilation went well. There are no warnings. This is the initialized data. The initialized data will go to the data section. You have to instruct the compiler not to put this data in data section, rather in a different section, which we call it as a user-defined section. How do you tell the compiler to move this data into a different section? That you can do by using the compiler attribute. Let's go to the compiler documentation again, and here you have to go to variable attribute. Just search for variable attribute. Here it is, common variable attributes. And here you have to use section attribute, section name. Here it is. Normally the compiler places the objects it generates in sections like data and BSS. Sometimes, however, you need additional sections, or you need certain particular variables to appear in special sections. Yes, that is our requirement. We don't want to push that into data section. Rather, we want to push that into a special section. This is how you should use section attribute. Whenever you are mentioning any attribute in GCC, you have to use this prefix. That tells the compiler that you are imposing some attribute. After that, this is the syntax you have to use. Here, this is a variable a of type this structure, and the variable a is placed in this section. Compiler creates a section called duart_a, and it keeps that variable in this section. Special section will be created here. All right, you can see that they have used this right after the variable name. You can also follow this syntax. Let me just go back to my code, and here let's do that right after this variable name, or you can do at the end of the variable initialization also. Attribute, you have to open double parenthesis here, so let's do that. Double parenthesis, and you have to give the attribute name section. After that, you have to again open the parenthesis to give the section name. Let's do that. Let me create a parenthesis here, and here give the section name. I would give .isr vector, or any name you can give. So here this dot is not mandatory. I have just given for the convention. This is not required. This is a section name. That's it. Let's see whether it compiles fine or not. Let me just run make all. Yes, it compiles. Or you can cut this and place this here at the end of this variable initialization here. That also should work. Let's see. Yes, it works. Now let's run the command none abi object dump -h startup.o. Here it is. We created a new section, and its size is this much. That data didn't go into data section. This works, but I would keep this right after the variable name here. That makes more sense to me. Even you can use this section attribute with functions. For example, I can use the same attribute with this function reset handler. I can just give at the end of function prototype here. I can mention something like this. So now reset handler code is not placed in text section. It will be moved to ISR, or you can change this section name. Let's say some random section. You can see that before compiling, let's check the object dump. Text section was this much size, isn't it? And now let's do make. It went well. Let's check again. Here it is. A random section is created and that code is moved here. You can see the disassembly here. Disassembly of random section. The code is moved to random section. Let me remove this. Now let's continue our vector table creation, and the next one is NMI address. Let's do that. Here, let me just create one more entry and let's call it as NMI handler. NMI handler. Let me use this capital. We have to create the NMI handler. We just created the NMI handler and let's add the prototype of this. Like this, you have to do for all 15 system exceptions and for 82 IRQs. That would be a tedious process. So would you create 97 such functions? That is not required actually, because in the program or in the application, the user or the programmer may not be using all the system exceptions or all the IRQs in the program. So he may be using few. That's why creating 97 such functions doesn't make any sense. That's why we can follow one shortcut. We can create a common handler for all the system exceptions and IRQs. Let me call it as a default handler. Instead of NMI handler, I'm going to create a default handler. And let's make this as an alias for all the exception handlers. For that, you have to use the GCC attribute weak and alias. What is a weak attribute? Weak is a GCC attribute lets programmer to override already defined weak function, or also called as dummy function, with the same function name. And the alias attribute lets the programmer to give alias name for a function. Let's use that. What I do here is I use the attribute with the NMI handler. Just watch this. It's very clear. Attribute, double parenthesis. So you just have to use alias. If you want to know the syntax of this attribute, you can refer to the documentation alias. Here it is. This is how you should use. You have to create one parenthesis and that you have to give the name, alias name. Let's do that. Let's create one more parenthesis. And here, let's give this name, default handler. Whenever you use the ampersand NMI handler, instead of this symbol, that is NMI handler, this symbol will be used. That means the address of default handler will be stored at this location, because this is the alias symbol for this symbol. What is next? So the next one is hard fault. Let's create the hard fault entry. Let me copy and paste this and let me call it as hard fault. This also has the same function prototype. Whenever NMI exception happens, the default handler will get called. Here, let's simply hang here. This default handler doesn't do anything, just it hangs in infinite loop. And whenever a hard fault exception happens, then also this function will get called. That means this is a common function, or you can also call it as a dummy function. Now, as I said, this is a dummy function. How to implement a real function which handles NMI exception or hard fault exception separately? That is done by the programmer. What programmer can do is he can override this function in his source file, and he can write the real code there to handle the NMI or hard fault exception. That's why what you have to do is you have to make this symbol as weak. We have to use a weak attribute here. Making this as a weak symbol gives control for the programmer to override these functions. He can create a function with the same name without giving any weak attribute. In that case, it is like overriding this function. For example, in the main.c, what you can do is you can create your own NMI handler and you can implement your real logic of handling NMI. Don't use any attribute here. Whenever NMI exception happens, control will not go to default handler. Why? Because this is attributed as weak. It goes to its real implementation, which is there in the main.c, let's say. That's why this symbol name and this symbol name, what you have used here, should be same. This is just the overridden function of this function. So now you have to create such prototypes for all the exceptions of the microcontroller and then populate in this array. That I will leave you as an assignment. What you can do is you can download a text file which I have attached with this lecture, and there I have mentioned all the prototypes of the exception handlers. Then copy that details into this source file and then update this array. I hope you can do that. And also you should note that whenever you are creating vector table, in the place of reserved, you have to put 0. That has to be maintained. This reserved space should be respected. You should create that gap in the array and put zeros there. I hope you can do that. Hey, welcome back. I just completed creating the vector table entries. It starts all the way from reset handler and it ends at FPU underscore IRQ handler. As you can see that in our vector table, reset is the first one and last one is FPU global interrupt. This may not be same in some other microcontrollers. You have to refer your vector table. Some microcontroller may have more peripherals. That's why according to number of peripherals in the microcontroller, this number will change. This is a vector table and these are the prototypes. You can see that by default, all are getting redirected to default handler. That's the alias name. For the reserved system exceptions or interrupts, you can keep zeros here. We finished this one, creating a vector table. And the next job is write a startup code which initializes .data and .bss section. This we are going to do in the reset handler, because reset handler is a first function which gets executed whenever the processor undergoes reset. That's why we are going to write this code in the reset handler. After that, we can call main. Here, copy .data section to SRAM. After that, next thing is initialize the BSS section to 0 in SRAM. And after that, call main. Before that, you may have to call init function of standard library. This is required only if you are using standard library in your code. For example, if you have used printf, scanf, or any string related standard library functions, then you have to call init function of standard library. Otherwise, standard library functions will not work. But for this exercise, we will omit this because we will not be using any standard library code in this exercise. Later we'll see how to do that, but for this exercise I'm not going to use any standard library code at all. That's why we can directly call main here, no problem. Now you have to do data copy, right, from flash to SRAM. How do you know the boundaries? You need to have these boundary information, isn't it? Boundary information and size information. Without knowing this boundary information, you cannot code those data copy things. That's why these boundary information have to be exported from linker script to your startup file. Then you can able to implement data copy things in the startup file. That's why in the next lecture, Let's write the linker script, and we are going to run some linker commands to link or merge all these different sections of the object file to create a final executable. That's it for this lecture, and let me know if you have any questions. And if you have any doubts, don't worry, while writing linker scripts, it will get cleared. I will see you in the next lecture.